Imagine a machine that eats a number and spits out exactly one new number. You feed it a 2, it gives you a 4. Feed it a 3, it gives you a 9. That machine is a function. We give the input a name, usually x, and the output we call f of x. The bef is just the machine's name, and the parentheses mean a feed this in. So f of 2 equals 4. The rule is, whatever you put in, square it. Every input has one and only one output. That's the one rule a function must follow. Why do we care about a number-eating machine? Because the world is full of relationships where one thing depends on another. How far you travel depends on how long you walk. The area of a circle depends on its radius. A function captures that dependency. It's a promise: tell me the input, and I'll tell you the output. If you can write that rule, you can predict anything. That's what science and engineering are built on. Let's build the function f of x equals x squared from scratch. First, the domain. That's just a fancy word for all the numbers you're allowed to feed in. For x squared, you can square any real number, so the domain is all real numbers. Now the range, that's all the numbers that can come out. Squaring never gives a negative, so the range is 0 and all positive numbers. To see the rule, we make a table. Input -2 gives 4, -1 gives 1, 0 gives 0, 1 gives 1, 2 gives 4. Plot those pairs as points on a graph, input along the horizontal, output up the vertical, and connect them. That curve is the picture of the function. Let's use our function machine to solve a real problem. Suppose you're tiling a square floor. The area depends on the side length. That's a function. Let's call the side length s, our input. The rule is area A of s equals s squared. What if the side is 5 meters? Feed 5 into the machine. 5 squared is 25. So you need 25 square meters of tile. The domain here is all positive side lengths. A negative side doesn't make sense for a real floor. The range is all positive areas. Same function, same graph, just a real-world lens. Imagine you have a set of building blocks. Before you build a castle or a spaceship, you need to know the basic block shapes. In the world of functions, these basic blocks are called parent functions. A parent function is the simplest, most stripped-down version of a type of function. It has no extra numbers added, no multipliers, and no shifts up, down, left, or right. It's the pure, raw shape. Think of it as the original mold from which a whole family of functions is made. Just like a plain brick is the parent of a brick wall, the function f of x equals x is the parent of all straight-line functions. We're going to meet 6 of these fundamental shapes today. Why do we care about these simple shapes? Because once you know them, you can understand any complicated graph at a glance. When you see a weird equation like 2 times the quantity x minus 3 squared plus 4, your brain will instantly say, that's just a parabola that's been stretched, shifted right, and lifted up. You'll see the parent shape underneath. This is a superpower for calculus. It lets you predict where a graph goes up, where it goes down, and how it behaves at extremes, all without plotting a single point. These 6 shapes are the alphabet of graphs. Learn them now, and you'll be reading whole sentences later. They are the raw clay we will soon mold by stretching, squishing, and sliding them around. Let's meet the family. First, the identity function, f of x equals x. It's a straight line slicing right through the origin, making a perfect 45-degree angle. Every input equals its output. Next, the square function, f of x equals x squared. This is the famous U-shaped parabola. It touches the origin at its very bottom, called the vertex, and is symmetric on both sides. Notice how it curves up gently. Then we have the cube function, f of x equals x cubed. This one twists through the origin, going down on the left and up on the right, like an S shape. The absolute value function, f of x equals the absolute value of x, makes a sharp V. It takes any negative input and snaps it to a positive output, creating that perfect point at the bottom. These shapes aren't just abstract ideas, they model real things. Imagine you're building a square patio. The area of the square is the side length squared. If you plot side length on the x-axis and area on the y-axis, you get our parent parabola, f of x equals x squared. A side of 3 feet gives an area of 9 square feet. Now think of a cubic box. Its volume is the side length cubed, giving us the S-curve of f of x equals x cubed. A side of 2 feet gives a volume of 8 cubic feet. Suppose you leave your house and walk in a straight line for 3 seconds, then turn around and walk back. Your distance from home over time is an absolute value V shape. At time t equals 3, you're at the peak distance, and the graph makes a sharp point as you change direction. Imagine you have a picture of a parabola on a piece of paper. Now you slide the whole paper up or down on the table. The U-shape doesn't change at all, it just sits higher or lower. That is exactly what a vertical shift does to a function's graph. We take the function, like f of x equals x squared, and we add a constant k outside, f of x plus k. This adds k to every single y value the function produces. If k is positive, say plus 3, every point moves up 3 units. If k is negative, say minus 2, every point moves down 2 units. The shape, the width, the way it curves, all of that stays exactly the same. Only its vertical position changes. Why would we want to slide a graph up or down? Think about measuring the temperature outside over a day. The shape of the temperature curve might be a nice wave, but the whole curve sits higher in summer and lower in winter. That's a vertical shift, the same shape, just moved up or down by a constant amount. In physics, if you throw a ball upward, its height follows a parabola. But if you throw it from a balcony instead of the ground, the whole parabola shifts up by the height of the balcony. Vertical shifts let us take a basic parent function and quickly adapt it to a real situation where things start from a different baseline. It's also a key trick in solving equations. If you can shift a complicated graph to make it cross the x-axis, you can find solutions more easily. Let's see exactly how this works with our parent parabola, f of x equals x squared. Its graph is a U-shape with the vertex at the origin, 0, 0. Now we add a constant k, say plus 3, right outside the function. The new function is g of x equals x squared plus 3. What does this mean? For any input x, we first square it, just like before, and then we add 3 to the result. So the old point at x equals 0 gave f of 0 equals 0. Now g of 0 equals 0 squared plus 3, which is 3. The old point at x equals 1 gave f of 1 equals 1. Now g of 1 equals 1 plus 3, which is 4. Every output is exactly 3 more than before. On the graph, every point moves straight up by 3 units. The vertex, which was at 0, 0, moves to 0, 3. Let's use a vertical shift to solve a real problem. Imagine you're setting up a small satellite dish. The dish's curved shape is a parabola, and its equation is y equals 0.1x squared. The receiver, which collects the signal, sits at the focus, right above the vertex. The vertex is currently at ground level, y equals 0. But you need to mount the dish on a stand that raises the whole thing 2 feet off the ground. How does the equation change? We simply add 2 to the output of the original function. The new equation is y equals 0.1x squared plus 2. Now, when x is 0, y is 2, the vertex is at 0, 2 feet up. Every other point on the dish is also exactly 2 feet higher than before. The shape of the dish, its curvature, the way it focuses signals, none of that changes. The vertical shift just lifts the entire dish to the right height. A horizontal shift takes a parent function's graph and slides it left or right along the x-axis without changing its shape. It looks like f of x minus h. The counterintuitive part is the sine x minus 2 shifts the graph to the right, while x plus 2 shifts it to the left. Think of it as the graph chasing the input value that makes the inside 0. The square root graph, for example, normally starts at 0. After shifting, its starting point moves, but the curve itself stays exactly the same. Horizontal shifts let us model things that happen earlier or later in time. If a parent function describes a process starting at time 0, shifting it right models a delay, like a rocket launching 2 seconds later than planned. Shifting left models an early start. In the IIT-JEE, you will constantly shift graphs to find where they cross axes or meet other curves. Mastering this now makes stretches, reflections, and combinations much easier later. Here is the trick that makes the direction click. When you see f of x minus h, ask, what x makes the inside equal to the old 0? For the square root parent, the starting point was at x equals 0. In f of x minus 2, you need x to be 2 to get the square root of 0. So the whole curve has moved 2 units to the right. For f of x plus 2, you need x equals negative 2 to get that same 0, so the graph shifts 2 units left. The graph chases the input that restores the original output. Imagine a Ferris wheel that normally starts at time 0. Its height above ground in meters is 10 plus 9 times the sine of pi t over 15. If the ride starts 3 minutes late, the height function becomes h of t minus 3. To find your height at t equals 5 minutes for the delayed ride, plug t equals 5 into the shifted function. That gives 10 plus 9 times the sine of pi times 2 over 15. The sine of pi times 2 over 15 is about 0.41, so 9 times 0.41 is about 3.7, plus 10 gives roughly 13.7 meters. The same method shifts any function to model real-world delays or early starts. We already know how to slide a graph up, down, left, and right. Now we're going to change its shape. Imagine taking the graph in your hands and pulling it taller or squeezing it flatter. That's scaling. Or imagine flipping it over like a pancake. That's reflection. We do this by multiplying. If we multiply the whole function, the output, by a number, we stretch or compress vertically. If we multiply just the input x by a number b, we stretch or compress horizontally. And if that number is negative, the graph flips over an axis. So with 2 simple multipliers, we can completely reshape any parent function we've already learned. Why learn to stretch and flip graphs? Because the world rarely gives you a perfect, simple parent function. Think about a company's profit over time. Maybe it starts looking like a V-shape, an absolute value graph. But what if the profit grows twice as fast as the basic model? You need to stretch it vertically. What if, instead of profit, you want to show a loss? You flip that V upside down, reflecting it across the x-axis. Or imagine you're converting a graph from seconds to minutes on the time axis. That's a horizontal compression. These operations let you take one basic shape and adapt it to fit countless real situations, from physics to finance. Let's see exactly how these multipliers work, starting with the absolute value parent function, that V-shape. When we multiply the whole function by ear, we change every y coordinate. If it is 2, every y is doubled. The point at x equals 1, which was at y equals 1, jumps to y equals 2. The v gets twice as tall. It's a vertical stretch. If a is 1/2, every y is halved, so the v gets squashed down. Now, if a is -1, every positive y becomes negative, and every negative y becomes positive. The whole v flips upside down, pointing up instead of down. That's a reflection across the x-axis. For horizontal scaling, we multiply the input x inside the function. This feels a bit backwards. If b is 2, we now have f of 2x. To get the same output as before, x only needs to be half as big. So the graph squishes inward toward the y-axis. It's a horizontal compression. Let's solve a concrete problem. A satellite dish is shaped like a parabola. Its cross-section can be modeled by our parent function y equals x squared, but it's much wider and shallower. Suppose the dish is 2 meters deep and we want to find its width at the top. We start with the parent function, but we need to stretch it horizontally to make it wider. A horizontal stretch by a factor of 10 means we multiply the input by 1/10. So our new function is y equals 0.1x, that whole quantity squared, which is 0.01x squared. Now, the dish is 2 meters deep, so we set y equal to 2. We have 2 equals 0.01x squared. Dividing both sides by 0.01 gives us x squared equals 200. Taking the square root, x is about 14.14 meters. That's the distance from the center to one edge. The total width is twice that, about 28.28 meters. We just used a horizontal stretch to design a real satellite dish. We have learned how to slide a graph up, down, left, and right, and how to stretch or flip it. But what if we want to do all of those things at once? That is what combining transformations is about. It is a single recipe that takes a parent function, like our familiar x squared parabola, and applies a whole sequence of moves to it. We write this recipe in a special general form, a times f of b times x minus h, all plus k. Think of it as 4 knobs we can turn. The h knob slides the graph left or right. The b knob stretches or squashes it horizontally, and can also flip it. The a knob stretches or squashes it vertically and handles the vertical flip. And the k knob slides the whole thing up or down. Our job is to learn the correct order to turn these knobs so the graph ends up in exactly the right place. You might wonder, why not just take the parent function, pick a bunch of x values, apply all the changes to each point, and plot them? You could, but that is slow, and it does not give you a feel for the whole shape at once. The real power of this recipe is that it lets you look at an equation and instantly picture the final graph in your mind. It also matters because the real world is full of shapes that are shifted and scaled versions of simple curves. A satellite dish is a shifted and stretched parabola. A sound wave picked up by a microphone is a shifted and scaled sine wave. And there is a trap here: if you apply the 4 knobs in the wrong order, you will get a completely different graph. Imagine sliding a picture on your phone before you zoom in versus after. The result is not the same. We need a rule that always works. The golden rule is, we always work from the inside out, starting with what is closest to the x. Think of it like getting dressed. You put on your shirt before your jacket. Here, the x is the body, and the operations closest to it happen first. Step 1 is the horizontal shift, controlled by h. We replace every x with x minus h, which slides the graph h units to the right. Step 2 is the horizontal stretch or reflection, controlled by b. We multiply the x by b. If b is bigger than 1, it is a horizontal compression, squeezing the graph inward. If b is between 0 and 1, it is a horizontal stretch, pulling it outward. A negative b also flips the graph across the y-axis. Step 3 is the vertical stretch or reflection, controlled by a. We take the whole output of the function and multiply it by a. Let us put this to work with a concrete example. We will transform our parent parabola, f of x equals x squared, into the new function -2 times x plus 3 squared, plus 4. First, we must match this to our general form, a times f of b times x minus h, all plus k. To see the h clearly, rewrite the inside as x minus -3. So h is -3. Step 1, horizontal shift. We replace x with x minus -3, which is x plus 3. This slides the whole parabola 3 units to the left. The vertex, originally at 0, 0, moves to -3, 0. Step 2, horizontal stretch. Here, b is just 1, so there is no horizontal stretching or squeezing. Step 3, vertical stretch and reflection. A is -2. The 2 means we multiply every y value by 2, so the parabola becomes narrower, growing twice as fast. The negative sign flips it upside down, so it now opens downward. Imagine you have a perfect clay mold of a parabola. You can slide it across a table, stretch it taller, or flip it upside down. The fundamental curve is still the same shape. In math, transformations let us take one parent function, like x squared, and shift or stretch its graph to create a whole family of related curves. They all share the same basic DNA. This is powerful because if we understand one deeply, we understand them all. We call this the family of curves idea. In calculus, the big ideas are finding the slope of a tangent line and the area under a curve. If we do the hard work to find the slope of x squared at x equals 2, transformations let us instantly know the slope for any shifted or stretched version, like 3x squared plus 5, without starting over. It is like knowing the recipe for one cake and then just scaling the ingredients for a bigger or smaller one. This connects algebra to calculus. It means we can model a cannonball's height with a transformed parabola, where the shift tells us where it was launched from, and the stretch tells us how strongly gravity pulls on it, and then use calculus to find its speed at any moment. Let's see why this works. A vertical stretch, like multiplying a function by 3, makes every point 3 times taller. Imagine a tiny right triangle under a tangent line. Stretching the graph vertically also stretches the triangle's height 3 times, but its width stays the same. Since slope is rise over run, the slope also triples. For area, think of summing many thin rectangles under the curve. If every rectangle's height is tripled, the total area triples too. A vertical shift, like adding 5, simply lifts the whole graph. The slope, which is a difference in y values, stays exactly the same because the added 5 cancels out. The area under an infinitely long curve changes, but for a finite section, the added area is just a simple rectangle we can add on. Let's model a ball thrown straight up. Its height after t seconds is about -5t squared plus 20t plus 1. This is just the parent parabola t squared, but flipped upside down and stretched vertically by 5 for Earth's gravity, shifted right by 2 for the throw speed, and lifted up by 1 for the launch height. We want its speed at t equals 2 seconds, which is the slope of the tangent. We know the parent t squared has a slope of 2t at any point. The vertical stretch by 5 multiplies that slope to 10t. The shift does not change the slope. So at t equals 2, the speed is 10 times 2, which is 20 meters per second upward. The whole idea is, master the parent, and transformations give you the rest of the family for free. Imagine you have a simple starting shape, like a parabola, and you want to place it anywhere on a graph, at any size. The transformation toolkit is exactly that, for basic moves you can do to any parent function. You can slide the whole graph up or down, which is a vertical shift. You can slide it left or right, a horizontal shift. You can pull it taller or squash it flatter vertically, and you can stretch or squeeze it horizontally. You can even flip it over an axis. All of these moves are captured in one general form, a times f of b times x minus h, all plus k. Each letter controls one specific move, so once you know the toolkit, you can read that form like a recipe. In calculus, you are constantly asking questions about a function's behavior. Where is it heading? How steep is it? What area does it enclose? If you have to plot every function point by point, you will be too slow. The transformation toolkit gives you instant recognition. When you see something like 2 times the square root of x minus 3 plus 1, you don't see a mess of symbols. You see the parent square root graph, shifted right by 3, stretched vertically by 2, and lifted up by 1. You can immediately picture its starting point, its general shape, and how it grows. This fluency lets you focus on the calculus concepts, limits, derivatives, integrals, instead of getting stuck on the graph itself. It is the visual language that makes everything else in this course easier. The toolkit works because the general form splits into 2 groups. Everything outside the function, the and the k, acts directly on the y values, so they move the graph vertically. A positive k lifts the whole graph up, and a bigger than 1 stretches it taller. Everything inside the function, the b and the h, acts on the x values, so they move the graph horizontally. But here is the twist: horizontal moves feel backwards. If you see x minus h, the graph shifts to the right by h, not left. If b is 2, the graph squeezes inward by a factor of 1/2. This happens because you are altering the input before the function sees it. To build any transformed graph, you apply the inside changes first, the horizontal ones, and then the outside changes, the vertical ones. This inside-out order always works. Let's use the toolkit on a real throw. Imagine you toss a ball from a height of 2 meters, and it reaches its highest point, 4 meters up, exactly 3 meters away from you. The path is a parabola, so our parent function is x squared. We need to move its vertex from the origin to the point 3, 4. That is a horizontal shift right by 3, and a vertical shift up by 4. So far we have f of x minus 3, plus 4. The ball also starts 2 meters high, not at ground level. At x equals 0, the throw point, our transformed function should give a y value of 2. Plugging 0 into x minus 3 squared plus 4 gives 9 plus 4, which is 13, way too high. We need to stretch it downward, so we multiply by a negative to flip it and make it open downward.